Wow, this will be our first chance to talk physics in person since the before times.
Yeah, I've been stuck in my room since, a year and a half now.
Obviously, theoretical physics takes place on nature trails and with enormous pieces of paper and Sharpies upon which to write equations. The physicist's laboratory is nature.
What our research group does is quantum information theory, which is a subject that often doesn't lend itself well to visualization. However, what we're fundamentally after are remarkable shapes. Really where the math begins is crossing two lines. Now, when we cross two lines, well, they make angles, and it looks at first like they make four angles. Boom, 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 boom. But if you think about it for a moment, as some clever ancient Greek did back in semi-mythic times, this bit plus this bit is 180 degrees, and this bit plus this bit is 180 degrees. So this has to equal this, and likewise this bit has to equal this bit. So angles on the opposite sides of the intersection are equal, meaning that we can talk about the angle made by two intersecting lines, because there's really only one number that has to be known. Everything else follows. It's either equal or 180 degrees minus that. What we seek are sets of lines such that the angle made by any pair is the same as the angle made by any other pair. We call these equiangular lines. For example, I could throw another line in like that. Now we have this angle, and 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 this angle. For each pair of lines, we have one number as the angle separating them. And, well, on a flat surface, it's pretty easy to see that we can make three lines such that the angle made by any two of them is the same as the angle made by any other two.
So the maximum number of equiangular lines that we can form in 2 dimensions is 3. What about when we look at higher dimensions? Let's consider the next larger dimension, 3.
Alright, let's experiment. Give me some branches, you'll have some branches. How about you? Just like that, and then now add
Make 2 crosses and then have them
you know.
We need computer graphics.
Matt, can you just give us a regular icosahedron? Thanks, Matt. This is a regular icosahedron, a platonic solid with 20 faces and 12 vertices which come in opposite pairs. These 6 diameters make a set of equiangular lines, the largest possible set in 3 dimensions. But we saw that in dimension 2, it was pretty apparent that the maximum number of equiangular lines we could arrange is 3, and no more. Up in dimension 3, with a little help, we found that the maximum number of equiangular lines was 6. In dimension 4, Well, that breaks our brain to visualize, but we can do it with Cartesian coordinates. You just add on an extra coordinate after x, y, and z. You find that the maximum number of equiangular lines is again 6. In dimension 5, adding one more coordinate and doing the math, they cracked it and found you could get 10 equiangular lines and no more. In dimension 6, the maximum number jumps up to 16. In dimension 7, it jumps up again to 28. In dimension 8, you're stuck at 28 again. No evident pattern in these numbers. You can play guess the number that comes next and not have a lot of luck at any point in this sequence. As one mathematician described it to me, it's essentially trench warfare, dimension by dimension, to find the answer, the maximum number of equiangular lines as a function of dimension. But everything we've said so far has been in the world of the real numbers. That is the familiar number line. And the coordinates of the points that specify where these lines go are all your regular numbers living on the ordinary number line. We can mathematician up the problem in another way by asking what happens if instead of using the real numbers, we use for our coordinates the complex numbers. That is, numbers involving things like the square root of -1. You've met these if you've plotted the Mandelbrot set, or if you've done alternating current in electrical engineering. Despite the name, they are quite useful and familiar as mathematical entities. Now, one can again pose the question, how many equiangular lines can there be in a space of so and so many dimensions, with those dimensions being complex valued coordinates? In 2 dimensions, the maximum number of equiangular lines, complex version, turns out to be 4. In 3 dimensions, the maximum number jumps up to 9. In 4 dimensions, it jumps up again to 16. In 5 dimensions, we find 25. Your pattern recognition sense may be tingling by now. In dimension 6, we find there are 36. In dimension 7, we find the maximum number is 49. Now it's definitely starting to look like a pattern, especially when we look at dimension 8, we find the maximum is 64. And by computer investigation, this pattern has been checked and confirmed to dimension 193 and counting. So it is apparently a very robust pattern. In the complex case, the maximum number of equiangular lines in a given dimension is simply the square of that dimension. Compare that to the real case, where there seemed to be a very irregular sequence with no evident pattern at all. Now, this pattern has not been verified out to infinity. We haven't had an infinite amount of computer time. There's no theorem that says it always must be true, but there's no case where it breaks either. So the reason this becomes a physics problem and not just a pretty little geometry question is that quantum mechanics uses complex numbers all over the place. By the rules of quantum theory, a maximal set of complex equiangular lines specifies a quantum measurement. Like an action you could go into the laboratory and do upon a system you care about. Each line in the set corresponds to a possible outcome of that measurement. So if you have a set of 4 lines, that's a measurement with 4 possible different outcomes. Moreover, these measurements are what we call informationally complete. That is, if you have probabilities for what could happen, and when you do this measurement, you can use those to calculate the probabilities for what might happen if you do any other measurement instead. Can you get both the hawk and me in frame?
Oh.
There are other measurements allowed by quantum theory which are informationally complete, but the ones derived from equiangular lines are, in quantifiable ways, the nicest, giving the cleanest possible expression of that translation from probabilities for one measurement to probabilities for another. And so, because of the equiangularity property, we give them the elevated name of the symmetric informationally complete quantum measurements, SICs, or Seeks to their friends.
We can take the regular way probabilities are calculated in quantum theory and find a new expression of the so-called quantum state in terms of probabilities for an informationally complete reference measurement. This gives us a new way of writing the basic equations of quantum theory that most neatly brings out the contrast with classical physics. Searching for and understanding Seeks has opened up entirely new areas of mathematics that physicists had not thought to explore before.